Hi everyone, welcome to our seminar. Today we are very happy to have Anson from the University of Maryland. Today he's going to talk about an interesting topic, which is the production of monopoles from evaporating black holes in the early universe.
Yeah, thanks for having me. So as was said, I'm going to be talking about basically how black holes can be producing monopoles in the early universe and some of the surprising things that result from it. People should feel free to ask questions in the middle of the seminar and just interrupt me. And so I think it's needless to say, people are pretty excited about black holes these days. Just like essentially the main start was due to LIGO seeing tons and tons of black holes. I'm sure that this is out of date by now, but this was a sort of a list of all the all the black holes they have seen, and even some of the neutron stars. And as a result, sort of not just astrophysicists, but also like particle physicists have sort of been interested in black holes again. And there's a ton of things you can sort of do particle physics wise with black holes, right? Dark matter, you can sort of study electric and magnetic charges on black holes, which are kind of interesting. Study their spin, because extra new particles sort of change things, let's say like the spin or how they were generated also will affect what their initial spins are. And there's been a fun industry also constraining new physics using black holes. There's a whole slew of things. And so, but today what I'm actually going to be talking about is sort of black holes in the early universe. So basically, if there were primordial black holes, essentially before CMB, and just ask what do they do to the world? And in fact, black holes in the early universe have been around long before LIGO. And in fact, originally, people thought black holes in the early universe were a problem. This is sort of how you know that these people who are talking about hybrid inflation were not really lying to you and trying to do this because they thought it was a problem when they were like, oh no, this is a problem. We generally cause too many black holes in the early universe. And so they genuinely thought it was a problem. Of course, it's not really a problem because black holes evaporate. And so the black holes, even in the early hybrid inflation, you form a ton of black holes. In fact, a lot of the times your entire universe is nothing but black holes, but eventually they evaporate and you just get a thermal bath, right? Because as famous from Hawking, sort of black holes are thermal objects that are radiating with a temperature equal to 1 over the radius. And you just get Stefan-Boltzmann evaporation. So they start getting smaller and smaller and eventually hotter and hotter because they have negative specific heat. And then eventually they evaporate, and then you have a radiation dominated universe, standard universe afterwards. And black holes are interesting because as they evaporate, they get hotter. This is the negative specific heat I just mentioned. So they actually probe all temperature scales in some way. And so you can ask then sort of, great, what do black holes, this is how black holes evaporate normally. This is what people study just in the vacuum. But in the early universe, it's not necessarily a vacuum, right? You might be black hole surrounded by a plasma, or maybe a black hole just surrounded by decay products of other black holes and things like that. And so you can ask, how does this change the picture, right? Because I'd say, how does evaporation in the early universe change? And so you can just say, well, if you have something hot surrounded by a plasma, how does that behave? And if you have a fireplace, you know how it behaves, right? You have some hot object in the center and it gets colder further and further away, right? This is how hot things behave. And black holes are very macroscopic, heavy objects. So comparing them to something, let's say a log, actually does make sense. You shouldn't think of them as particles. And so this is really how you should think about a black hole in the early universe. You should say, in the early universe, there's a black hole. And as you get further and further away from it, you go from hot, very hot, to colder and colder. And then if you get far enough away, you're basically at the temperature of the bath, which is surrounding it. And it turns out that this radius is actually extremely large. So when I say like it's surrounded by some hot plasma, this hot plasma has radius many times larger than the radius of the black hole. So even though the black hole itself is some small hot object, its sort of sphere of influence is much, much larger than the radius of the black hole itself, right? This is just exactly like how burning a log works, right? It's not, you're not sticking your hand in the fire to get warm, you're just standing nearby. And so I'll get to it later, but black holes are basically surrounded by a plasma, and this plasma can get within 1% of the temperature of the black hole. So if this thing has gut scale temperatures, right, it's evolved small, temperatures around it are maybe 1/100th of the gut scale, so still super huge. And so it could be actually very important. And not only that, after the black hole disappears, it takes some time for this hot region to cool down. And this cooling process could also be very important because the time it takes for this thing to cool is actually longer than the lifetime of the black hole. So it actually takes a long time to cool. And so it stays hot for a very long time, longer than the lifetime of the black hole. So of course you can ask, is any of this important? And the answer is, well, again, from the example of a fireplace, we know that sometimes the area around this hot object is more important than the hot object itself. And so actually, you can ask then, is this hot plasma surrounding the black hole, can it be more important than the black hole itself, right? So could it be that the only important thing that the black hole is doing is providing energy into the system and heating it up? And the answer is yes. And what I'm going to talk about today is basically production of monopoles. And monopoles will be an example of a situation where the plasma is much more important than the black hole itself. Okay, so, whoops. Very quick statement about monopoles is monopoles are pretty awesome. They can explain tons of things like the quantization of electric charge. They can do really cool things of catalyzing proton decay. It's the way they catalyze proton decay is also kind of odd. It's a sort of a weird, you might even say it's a violation of decoupling. It depends a little bit on your point of view. It's the only way we can measure the sort of topological theta angle of E and M. Otherwise, that topological angle is completely unphysical. And it's also sort of related to confinement and Higgsing. So in the normal case of a black hole evaporating in vacuum without a plasma, how does it produce monopoles? And the answer is not very much, because here we have a picture of, let's say, a large black hole and a slightly smaller monopole. Because the temperature is of order of the radius of the black hole, if the black hole is larger than the monopole, the emission of the monopole is exponentially suppressed by Boltzmann suppression because the temperature is below the mass of the monopole. Okay, that's to be expected. But what happens if the monopole or the black hole is hotter than the monopole? The answer is it's actually at that point, because monopoles are composite objects, the monopole is much larger than the black hole at this point. And so what you're asking for is some very small hot object to emit a huge thing, huge fluffy monopole. And the answer is, well, whenever there's an exponential sort of difference in size, there's an exponential suppression due to this. It's like saying, if you collide protons at the LHC, what's the probability of something like a pen flying out? And the pen is larger than the collision point. And even though you have enough energy maybe to create this pen, it's exponentially suppressed that you get this pen out, just because, forget like sort of cross-section calculation, it's just the physical sizes don't match up. And it's the same thing here. People have calculated monopole production by black holes that are hotter than the mass of the monopole. And the answer is it's also exponentially suppressed, exactly because of this difference in sizes. And so a black hole never produces a monopole. It's always exponentially suppressed, whether it's large or small, always exponential suppression. How does a plasma change it? The reason is, if there is a black hole hotter than the monopole, it produces a region of hot space. And this region of hot space itself could be larger than the monopole, because now the sphere of influence of the black hole is much larger. And hence you can actually have a hot region of space that's actually larger than the monopole. And so it can actually produce the monopole. And so that's basically what I'm going to be talking about today. It's just, how does this plasma surrounding it, like when a black hole slowly evaporates and then this region cools, how does this process produce monopoles? And it turns out it produces monopoles very efficiently, even. So that line of my talk is basically going to be, I'll first sort of review how to calculate the temperature profile around black holes, to basically talk about what happens when you heat up the plasma around the black hole, and then what happens as it cools down. And then I'll sort of remind people about how monopoles are produced in condensed matter systems or in hot thermal plasmas, which is the Kibble-Zurek mechanism. And finally, I'll sort of talk about how this actually, you can place bounds on, for example, reheating from black holes from this, and then conclude. All right. So I'm going to assume people haven't really done thermodynamics of a plasma before.
Can I just quickly interrupt? So one question is that you can produce them, but I'm sure you'll discuss this, so maybe this can wait. But then why would the monopoles escape? I mean, I assume you'll be doing monopoles, anti-monopoles.
Yeah, so actually what happens is when you don't actually produce monopoles while the black hole is still present. It's the cooling phase that happens afterwards.
Right.
So as this hot region undergoes a phase transition, you get Kibble-Zurek that produces the monopoles, but then it's cooling. So everything is leaving this area. And so you produce a bunch of monopoles, and then they're just sort of getting pushed out as you go. And for example, you can calculate scattering rates and show that they actually never even meet another monopole before heading off away from this hot area.
Okay.
And so it's not actually the heating process. It's actually the cooling process after the black hole is well gone. That's actually doing all the work.
Okay. All right.
Yeah.
Thank you.
Okay. So I'm going to basically give a quick description of how temperature evolves around a heat source. So I assume, well, maybe you guys are more educated than I was when I started this, but I didn't know basically the basics of how these equations work. And so I'm just going to describe quickly how they work. And so to derive the equations, let's just to make things simple, let's just say the temperature only varies in the z direction. And so you have it hot on the left and cold on the right. And you can ask, how does energy go through this? And so what the astrophysicists or stellar physicists will tell you is what you care about is something called the specific intensity. It's basically how much energy is passing through a unit area per unit solid angle, per unit time, per unit frequency. So a lot of per different things into this, but it's basically saying just the power going in some direction. And so you can say what happens if you have some power going through. You have the first term here, which is the absorption. This is just saying your medium could be absorbing light as you're shining it through. But then there's also emission, which is just saying, well, the hot plasma can also be emitting light in the same direction. And so there's two terms, basically absorption, emission, and then there's some cosine thetaology, basically due to the fact that you're not necessarily going directly in the direction of things changing. Okay, this is sort of your starting point. And what do you do with this starting point is you actually multiply both sides by cosine theta and integrate. Now, you can ask what happens. Well, the first term, well, let's look at the far right term, the sort of emission term. Thermal equilibrium emits isotropically, the same in every direction. So if you weight it by a cosine and integrate, it just gives you 0. So great, all you care about then is absorption. And what's the integral of cosine times your specific intensity? It'll probably take you a little time to think about it for a moment, but that's actually just the energy flux going in the z direction. This is saying the cosine theta basically gets you pointing in the right direction. Things are moving at the speed of light, so you don't need velocities. And so you basically just get the energy flux in the z direction. And then finally, on the far left side, what's the integral of cosine squared times the intensity? Again, you'll have to think for a moment, but this is actually pressure. And so what you get is that the energy sort of the transport of energy, the energy flux is just equal to the mean free path times the gradient of the pressure. And so if there's some pressure, stuff moves. Great. And units are made up by the mean free path. Sort of, if you had to guess, this is what you would guess. And the result of all this algebra is just saying the coefficient is 1 for that equation. And in fact, for thermal equilibrium, pressure is just a third of your energy density. This is the famous W equals 1/3 for radiation. And so you can say the energy flux is related to gradients of energy with a factor of 1/3 and the mean free path. But that's basically all we need to know, is that this is what the energy flux related to gradients of energy. And then one last thing that you sometimes will need is just conservation of energy, right? So the flux leaving tells you how much the energy density is changing, right? And so we can get rid of the flux because we know of energy flux in terms of the density itself. And so we just have a single equation here, which is basically all you have to do. And in some sense, at this point, you could just be like, game over, simulate a numerically solved black hole with these boundary conditions, and just saying, how do things change in time and how do things change in space? And so basically this one equation is all we need to know. It tells you how does the energy density change as a function of gradients. Great.
No, there aren't things like convection and all that you have to worry about.
Yeah, and so this is in the limit where things like convection and all that are not important. And so I'm going to assume that's the case. It's actually a bit of a microphysics question if that's actually a valid assumption. So for example, in stars, for example, this equation will sometimes be true, and sometimes you have to add in additional terms for convection and things like that.
Okay.
But this is at least two of the terms, even if you have to consider convection. Convection will just be a second term on the right-hand side here.
Nice. Okay.
And so we can look at this equation and say, okay, what does an equilibrium configuration look like? In particular, let's look at a hot object surrounded by plasma and just say, forget all time dependence. What is the equilibrium situation of this? And it turns out you could get the answer by solving what I just said, or, whoops, why? So first, you could just solve this equation to get it, but there's a quicker way to the solution, which is just saying in equilibrium, the energy leaving any radius is the same, right? It's equilibrium, all energy is being emitted the same. And so the energy being emitted at any given radius is just the area times the flux. So 4 pi r squared times J. If you just say everything has units of 1/temperature, so mean free path has units 1/temperature, gradient has units 1/r, rho has units of t to the 4th, you see that what's constant is r times t cubed. And contrast this to, let's say, Stefan Boltzmann, where Stefan Boltzmann is saying the energy emitted is just r squared t to the 4th. Here we're saying the energy emitted at each radius is RT cubed. And the reason why this is smaller is because there's radiation back inwards. When you have a hot region, you have radiation going out, but you also have the hot guys outside radiating back in, which is just different from standard black body radiation where there's nothing outside. So it's actually radiating slower. However, you can see then that RT cubed is a constant, which means that T scales is 1/r to the 1/3 power. So it's really falling extremely slowly. It's not 1/r, 1/r squared, which we're sort of used to. It's 1/r to the 1/3. So these temperatures fall extremely slowly. But one thing you should keep in mind is that you can ask, what is the energy of a configuration in equilibrium? And it's falling so slowly that it actually takes infinite energy to extend equilibrium to r equals infinity. And so if you have anything with finite time, finite whatever, finite energy, you're not going to have equilibrium forever. Eventually, there's going to be a radius where just like conservation of energy says you cannot be in equilibrium. And in fact, it's also, if you have finite time, energy diffuses away. It doesn't just travel in a straight line. And so there's also like a finite radius that comes from diffusion. Luckily, those two turn out to be exactly the same radius. So you can estimate all these radii by either doing conservation of energy or just diffusion time. They give exactly the same answer. Okay, but either way, thing to note is at some radius, equilibrium cannot hold. Okay, so let's finally get to the black hole. So what is the temperature profile around a black hole? And what I'm going to do is say, like I said before, you could just numerically solve everything. But as a theorist, I enjoy having analytic estimates. So I'm going to actually also tell you how to analytically estimate this. And then just say all the order one numbers come from some numerical solving of the differential equation. Okay, so what does the temperature profile around a black hole look like? So if you go right near the black hole, Hawking radiation has to thermalize with the plasma. And so it takes some time for the plasma to absorb the energy of the Hawking radiation. And so if you go too close to the black hole, you're not really in equilibrium with the energy being emitted. However, at some intermediate range, you have a plasma that's in equilibrium with the energy being emitted by a black hole. And then as you go further and further out, eventually you get a radius where, like I said, you can never be in equilibrium for infinite radius. So eventually at a far enough radius away, you're just not in equilibrium with a black hole. So too close, you can still be a hot thermal system, but you're not in equilibrium with the Hawking radiation. Further away, you're in equilibration with all the energy being emitted by the black hole. And then finally, there's a radius where conservation of energy is saying you're not in equilibrium. Okay, so this middle one is actually where I'm going to be focusing all the energy and saying this is actually where, for my choice of parameters, where I'm going to live, is just live in the place where you're in equilibrium and temperature is falling as 1 over r to the 1/3. So the very slow one. And again, that radius, I'm going to call it the fusion radius, but you can also just say conservation of energy. They give literally the exact same answer for what that radius should be. So what you do is in this region, I had said temperature falls as 1 over r to the 1/3. Can I do more details? Can I say what is R0, what is T0? And what you do is you just say, well, the energy being emitted by the black hole is equal to the energy being carried away by this thermal equilibrium, right? That's equilibrium. You can put order 1 numbers, but I'm sort of skipping that here just because like I said, order 1 numbers will just come from the numerical simulation. This is sort of a parametric analytic guess. And so if you just say the energy emitted by the black hole is equal to the RT cubed energy being emitted or transmitted by the plasma, you see that the temperature is basically T black hole to the 2/3 over R to the 1/3. So all the other dimensional analysis is being made up by T black hole, which makes sense. That's the only other dimensionful thing in the problem. So of course, dimensional analysis works. Okay, what about diffusion? So if you do combined diffusion, diffusion is basically saying R squared, the amount of time it takes for energy to diffuse out, is just free streaming length times time, right? This is how diffusion works. And you can ask, given the lifetime of the black hole, how far could the energy have diffused away? And you get some parametric estimate for the diffusion radius. If you combine this with the temperature profile I just mentioned, what you see is that the diffusion radius scales like temperature 1 over temperature of the black hole to the 11/5. The important thing here to notice is fine, and you got some order 1 numbers from doing some algebra, but is that it's proportional to 1 over T black hole, meaning that as the black hole evaporates, the diffusion radius is getting smaller and smaller. So what's happening is as the black hole evaporates, this freeze out location where you're no longer in equilibrium is shrinking. So just like in the early universe where you have freeze out as when things are comparable to Hubble, here's what's happening is just you're getting freeze out as a function of radius. So it's slowly moving in the freeze out radius as the black hole evaporates. So this is sort of how to think about what's physically going on. And then you can say, what is the temperature in the freeze out region? Well, you just say, well, its temperature is exactly at the point when it was in equilibrium and just about to freeze out, right? Just like how we do for whatever early universe cosmology, where you say freeze at number density is fixed exactly about when it's just freezing out. Here is the same thing. Its temperature is just when its temperature was freezing out. It's a little bit of math. It's not particularly important, but you just say that physical statement of just the temperature at any given radius is its temperature just as it was freezing out. And you find that in this frozen out region, the temperature is scaling like 1 over r to the 7/11ths. And interestingly, all the rest of the dimensions are being actually made up by m Planck here. So the initial temperature of the black hole didn't really matter. It's just when it froze out, it's just some very steep profile, but with m Planck making up the rest of the dimensions. And that's okay because the initial temperature didn't matter, because when freeze out happens, the temperature of the black hole is fixed by just saying diffusion limit, it's diffusion limited. Okay, but either way, this is sort of the analytic logic for how to get the temperature profile around it. You'll find out, for example, cooling and other things that would say that would change this frozen out profile are actually much longer than the lifetime of the black hole. So you can just sort of ignore all cooling until you get the full temperature profile and then talk about cooling afterwards.
Can I ask you a question, Anson?
Yeah.
So especially if we're thinking about these things in the early universe, why doesn't Hubble enter as a dimension full scale?
Excellent. So what I'm essentially interested at times roughly when Hubble is comparable to the initial lifetime of the black hole. But as soon as it starts to evaporate, its lifetime is decreasing. And then, so even if you start off with Hubble about equal to its lifetime, very quickly its lifetime is much shorter than Hubble. And so if you're interested in things very close to the black hole, it's actually happening on timescales much faster than Hubble. Does that make sense?
Yeah.
Yeah.
Can I just, so earlier you had an expression for this temperature as a function of R.
Yep.
And this is somewhat different. So this is at a time when the black hole has evaporated.
So this is basically, and there are the two equations governing these two regions, which is in between the red and the blue, where you're in equilibrium with the black hole, and another one of outside where the temperature is frozen out. And so those two temperature profiles are different. And so the first one I talked about, where was it? Here is in the part where you're in equilibrium with the black hole. And then I sort of said, well, eventually the black hole disappears. Eventually this diffusion radius shrinks to 0. So eventually everything is frozen out from the black hole. And so that's ultimately the only one I really care about.
I see.
And so that's this weird 1 over r to the 7/11ths. So a really odd power, but that's what you get just from doing these arguments.
Okay.
And yeah, anything else? Excellent. So let's just say, does anything I said supported by numerics? And so this is essentially what the temperature profile around a black hole looks as a function of time, just numerically solving the conservation of energy equations. And so from here, you basically said t equals 0 is this blue line. And then as you advance, getting closer and closer to the decay of the black hole, which is tau, when it's just completely evaporated. And so from this, you can notice a few things. First is if you look to the far left, which is really close to the black hole, it's not necessarily obvious, but the blue line here is I actually just started off with a profile of 1 over r to the 1/3. And you can see very close to the black hole, these sort of orange and blue, and to some extent the red, have this same slope. So close to the black hole, you have the equilibrium distribution of t goes to 1 over r to the 1/3. And so the sort of numerical simulation does confirm that near the black hole, you're in equilibrium. And then you can look at this other region here, which is the frozen out region, which is basically stopped changing. You can sort of see that as you go from green to red there, that value is not really changing. And if you go even further down, sort of as you go from orange to red, it doesn't change. And so if you just fit that part of the spectrum, you get this weird t goes as 1 over r to the 7/11ths. And then finally, you said this thing, was just my initial condition. It was never in equilibrium with the black hole to begin with. And so it just never changes throughout the entirety of the evaporation of the black hole. Basically, the black hole never had enough energy to change that guy there. Okay, and so if you just numerically simulate everything, what you get is that it depends on some model dependent factors like the cross section, the G stars to the 1/11th power. So basically it just doesn't care about your microphysics at all. And the order 1 number happens to be about 0.2. Okay, so great. The sort of analytic estimate roughly worked up to this 0.2 factor. Now let's talk about cooling. What happens? The black hole evaporates. Everything has reached this weird T to the 1/R to the 7/11ths. How does it cool off? And so what you can do is just say, given some radius you're looking at, say we know it emits energy at this RT cubed rate. Compare it to the total energy in the section to get a characteristic time scale for which it takes to cool off. And what you see is that the larger radii sort of cool a lot slower. That's not too surprising. Larger radii have a lot more energy. So of course they're going to cool more slowly. And so what you see is that you have a slow change, which is like the inside cools and then the outside cools a little bit and then the outside cools. And so essentially what you have is you have a radius within which it's cooled off. But what does it mean to have cooled off? It means it's reached a constant temperature. So you have this cooling radius, which is inside of which it's a constant temperature, and outside of which it just hasn't had time to cool off yet. And as time increases, this cooling radius increases slowly and slowly. And then the overall temperature is slowly going down to approach the asymptotic value. And so you can model this.
I'm a little puzzled by that.
Yeah.
Because the inside is hotter, so you would think that by cooling it would send its energy to the.
So that's an interesting thing about this 7/11ths profile. Where is it? Is if you actually calculate the energy inside a ball, it's dominated not by the center, but by the outside. So, so it's still IR dominated.
I see.
So even though it's this weird power, and it's not even 1/R, it still turns out to be IR dominated.
Okay.
So if you compare, what is it, like R cubed times T to the 4th, that scales R to a positive power. So all that energy is still in the large radii. And so even though the middle guy is cooling off, it doesn't have the amount of energy to increase to increase the temperature at higher radii.
Okay.
But you will see us actually in the numerical simulations, you do see a little bit bump where it does raise the temperature just outside a little bit, just because it doesn't have enough energy to really raise the temperature. It has it enough to just do a little bit of a bump.
I see.
Yeah. Where was this? Pretty far back. All right. And so we can sort of model this cooling is, roughly speaking, there's a constant region, and outside of which is the original 7/11ths profile, and inside is constant. And you can calculate how does the total temperature in the center decrease as a function of time, and how does this radius expand by just saying the energy being emitted is this RT cubed, set it equal to basically total energy over time, dimensional analysis, solve for how things depend on time. You go through this exercise, you basically see that the radius is cooling like some weird power of T to the 11/15, and the temperature in the center is cooling off as 1/T to the 7/15. So you get weird powers, but this is also actually what comes out of the numerical simulations. And so conservation of energy doesn't lie to you. You simulate it, and this is basically what you get is you just start off with some profile, and then you see like as you cool, like 2 times time, you see there's a center region for the yellow, green, and reds. There's a constant temperature region, and then you see at the far right, it's basically not changing until the temperature, this sort of radius is moving out. And you can sort of see what was alluded to earlier. There's a little bit bump as you sort of heat up the outer regions, but you don't really have the energy to heat it up by very much. And so it doesn't really, it changes a little bit, but not much. And then as you can tell, this is like time goes from 2, 10 to 100. It's taking a much longer to cool. And of course, you can just sort of do what I'd said before and just look at the constant temperature core, measure its temperature as a function of time, or measure this radius of cooling and see how is it expanding as a function of time. And you get some order 1 number, which is basically 0.1 in front. Now, this guy does depend a little bit more on your particle physics parameters, right? If your scattering length is very large, things cool a lot faster because it can travel very far and deposit its energy much further away. And so this C alpha is roughly speaking related to the cross section. And it depends a little bit on G star and a little bit, well, not much at all on these sort of black body factors. But you do get this weird T to the 7/15. And again, as before, you see that it depends only on M Planck as the other, making up the rest of the dimensional analysis. Okay, so this is basically how a black hole heats up and then cools down in the early universe, right? We're assuming that it's basically reaching equilibrium step by step. And roughly speaking, if you assume that everything is spherically symmetric, numerical simulations basically confirm everything. If you're not spherically symmetric, then you start running into issues like convection and whatnot. And so we're just saying, hopefully you're working with high enough temperatures or close enough to the black hole that spherical approximation is good. So let's get to monopoles. So Kibble-Zurek is basically how monopoles are created either in the early universe and in condensed matter labs, which is essentially what happens is the way we basically produce all topological defects is to heat something up and then let it cool down slower and slower. And what happens is that you get regions that are basically of size correlation length. And each correlation length chooses its own value. And by absolute random chance, you'll sometimes get some topologically non-trivial topologies. So it's basically, Kibble-Zurek is a way of producing topological objects like monopoles and strings by complete random accident. And roughly speaking, what you do is you get a topological defect per correlation length. There's a very uncertain order 1 number that depends on a lot of microphysics that I can't tell you what it is. People just experimentally measure what that number is in a lab. So I'm sure it's been a long time since people have actually seen more than word level Kibble-Zurek. So let's actually say, what were the equations behind Kibble-Zurek? And then we'll just put in all the numbers that the early universe tells us what those numbers are. Or, well, a hot plasma, sorry, not the early universe, just a hot plasma. And so Kibble-Zurek, they started off by saying, basically, what is the time to the phase transition? You'll say the characteristic time of the phase transition is your time 5 seconds from now when I have cooled to temperature equals T flat phase transition. And epsilon is basically how fractionally close you are to the phase transition. At the phase transition, I'm going to take it to be a second order phase transition, which means there's a massless particle. So all correlation lengths go to infinity at the phase transition exactly, because you've tuned it to be a massless particle, which means at the phase transition, correlation lengths and correlation times are equal to infinity. Now, how fast they approach affinity is they approach it as a power law, sort of basically whatever you expect from CFTs. And a power law to some power that I'm not going to tell you. It's some time approaches it with a power law of mu, length approaches it with a power law of nu. And then what they say is that everything freezes into place when the time to the phase transition is equal to the correlation time, right? Because then you're cooling it so fast, it doesn't have time to adjust. And so what Kibble-Zurek did was they just said, well, at this time, when the time to the phase transition is the correlation time, you can solve for everything, and you get what the correlation length is then is just some number. And they just say that is the regions of space after you've cooled to below the phase transition with which they've chosen the same value everywhere. And so it's a standard freeze out calculation. And in the early universe, what you do is you say, the sort of correlation length and correlation time is just 1 over the mass of some particle. We can Taylor in particle physics, right? In the Lagrangian, what appears is the mass squared. So your Taylor series, the mass squared, it's some linear term times t minus tpt. And so you just get characteristically 1 over tpt times this square root of epsilon, square root of how close you are. And so that just means that this mu and nu were 1/2, plug everything into what Kibble and Zurek did. And you get basically that correlation length is roughly 1 over the temperature of the phase transition times this sort of characteristic time times tpt to the 1/3 power. Now, so this is basically Kibble-Zurek, and well, Kibble-Zurek was, they basically said this was it, which is observed to be correct in the lab. The experimentalists will even tell you what the order 1 numbers are. In the early universe, you can use dimensional analysis to say what the parametric scaling is, at least. We have 0 idea what's the order 1 numbers, but let's just say that they're order 1 and proceed and see how things work. And the characteristic time is basically how long it takes to cool. But that was exactly what we had found from the cooling phase of the phase transition, right? We figured out analytically and numerically, how fast do these constant region temperatures cool? Like, what is the characteristic time? Now, normally in the early universe, people will say phase transition takes time of order Hubble, and so the characteristic time is Hubble. But now we're saying we're not doing some homogeneous thing. We're doing some right close to the black hole, which is heating and cooling on a scale much faster than Hubble, but faster than a very different Hubble than Hubble PT, because the universe is much lower temperatures. So that it's actually a much longer characteristic time here. So you just take what we did before, plug it in to the characteristic time here. And what you get is, if we say that, roughly speaking, you can take what we did before, which is we had this, look at exactly the time when the universe has cooled, or not the universe, but the hot region left over by the black hole has exactly reached TPT, and you ask how quickly does it move through it, and what is its radius? Because the number of monopoles is the radius cubed over the correlation length cubed. That's just order dimensional analysis. And you see that this is a huge number, right? This turns out to be m Planck over TPT to 4/7, so basically a half power. So if you're saying like m Planck is huge, so if you're saying I have, let's say, a non-SUSY theory, so unification is at like 10 to the 14, 10 to the 15 GeV. This is like order, 10 to the 4, this is order like 100 so monopoles being produced per black hole, as opposed to before, the black hole itself produces 0 monopoles, exponentially few, but the plasma itself produces hundreds of monopoles. And so you actually get tons of monopoles per black hole. And you can sort of calculate sort of scattering rates, because you might worry that you're producing monopoles and anti-monopoles. You can sort of confirm that there are not enough of them that they don't annihilate each other and disappear after they're produced. So what I'm going to do then is say, great, we have this way of producing black hole monopoles in the early universe from these black holes. What is an application for this? Well, I'm going to go back to the case of hybrid inflation, where basically there's the most black holes possible. So in other words, reheating of the universe happened via black holes, and ask what happens in that case, because then you have the most black holes possible. So you get the most monopoles possible. Does something happen? And so at the very beginning, so you imagine the universe has nothing but black holes after, let's say, hybrid inflation or something like that. And then around when Hubble is equal to the lifetime of these black holes, they start to evaporate. And so let's say like 50% of them evaporate, so that there's a concrete plasma around every other one of these, the remaining 50% of the black holes. Then you sort of can calculate what the reheat temperature is. It's some classic, easy to do calculation that I think even Hawking did. And because of the plasma surrounding these black holes, each black hole has this small temperature gradient around it. And then eventually the black hole keeps on evaporating and evaporating and disappears. And so then you just have a bunch of overdensities or hot regions. And as these hot regions cool through TPT, right? Because even though the reheat temperature could be much, much lower than the temperature of the phase transition, very close to the black hole, these were just M Plancks over radii. There was like nothing else, no TV heat appearing in any of these equations and so they just get extremely hot near these black holes. And so eventually you cool off, as you cool through the phase transitions, you get a bunch of monopoles. And eventually that's just the remaining monopoles. They sort of dilute away and that's it. And so you have a large number of monopoles, maybe order about 100 per black hole. What happens? Well, one thing you can definitely say is these black monopoles should have less energy in them than dark matter, right? That's like the 0th order stupidest thing you can do. And if you just even say that and say that they should have less energy than all that of the dark matter, you get that the reheat temperature has to be smaller than 700 GeV, which is just crazy. You have like barely restoring electroweak symmetry breaking, and you care about this phase transition happening at 10 to the 15 GeV, just because the black holes are heating up a tiny little bit of your plasma to a really hot temperature. But that still gives you such an efficient production of monopoles that you overclose the universe, right? You can barely do baryogenesis in this situation, right? It's like you barely get electroweak symmetry restoration. So it's really surprising, like if black holes are reheating the universe and you have a high temperature phase transition, you notice it depends only marginally on this, like 9 to the 35th, right? You got these really crazy power laws around the black hole, so you get kind of crazy powers here. But the numbers worked out that it's like, yeah, you're reheating to temperatures below a TV. That's just the way it is. If you believe in monopoles, at least. And the higher the phase transition temperature, the lower your reheat temperature has to be. So if guts, like 10 to the 16 GeV scale is where all the magic is happening, you need a really low phase transition temperature. But if you have maybe something more like Padi Salam or something else where it's lower scale unification, then you can actually tolerate much higher reheat temperatures. And so that's sort of like an interesting thing. It's just like, I would have never thought your reheat temperature could be at all correlated to these super high energy thing. But in the case of black holes, they really are. So of course, there are a lot of caveats that have to go in to just be like, when is my calculation valid? What are the order 1 numbers, et cetera? And so a quick caveat on what are the model dependent factors and how can they actually influence this thing. Remember I had said that, for example, the correlation lengths and correlation times are roughly 1 over the mass of some particle, but the mass of a particle depends on things like quartic couplings and things like that. And you might just say, I like quartic couplings of 10 to the minus 30 or something. And then that will drastically change your result, because if you have a smaller quartic coupling, you have much larger correlation lengths, which means you have much fewer monopoles. And so if you just go through a bit of algebra, you see the 700 GeV number scales like this quartic coupling to the 3/5. So if you change your quartic couplings by several orders of magnitude, you can sort of increase or decrease this reheating temperature. Another thing you can ask is just, what about the cross section? The cross section is something that, well, who knows what it is? It depends a lot on what I say the gut theory is. So if you just say the cross section is like some alpha squared over t squared, it depends on this alpha, or C, I'm calling it, I guess, C alpha, because it also depends a little bit on the number of final state particles, blah, blah, blah. It's not exactly the coupling constants. It depends on it to the first power, roughly.
So sorry, what was this cross section for? I mean,
this is cross section of scattering your typical particle. How far does it travel before it scatters?
Oh, I see. It's just the diffusion.
Diffusion, because if the diffusion length, it's a much more weakly couple, the diffusion length is much longer, which means it can cool faster, which means the bound will be weaker.
Okay, thanks.
And so my generic thing, for example, I'm like normal gut has alphas of 1 over 25 roughly. And so that's actually like the benchmark point I used. is just a standard gut number. But if for some reason or another you did a lot of Higgsing and things like that to just decrease couplings, or maybe you add a new strongly coupled sector, you can change this a little bit. The last thing, well, not the last thing, there's another caveat, which is we assumed that this hot region was larger than the size of a correlation length. And so you have to actually check if that's true or not. You go through a bit of algebra and you say that, well, this phase transition should be smaller than about 10 to the 16 GeV, which you'll notice is starting to get a bit close to the SUSY values, right? And so maybe for the SUSY unification, you might not have to worry as much about these things. Actually, a slightly stronger constraint happens because, like I said, the region most close to the black hole isn't in equilibrium with the black hole because the Hawking radiation just smashes through without depositing most of its energy. And so if you actually go through and calculate what is the temperature of the region right around the black hole, it's a little bit colder than the black hole because it takes some time for the Hawking radiation to deposit all of its energy. And it's roughly speaking 1% of the temperature of the black hole. And so if the temperature, if your TPT is close enough to M Planck, you just, none of it, you never reached that temperature, right? It's the thing around outside got to 1% of your black hole M Planck, but not quite to your TPT. Even though it eventually reached Planckian temperatures, the plasma surrounding it never reached Planckian temperatures. And so you see that this is actually a few times 10 to the 15, with some dependence on G star factors, on what is the weak coupling constants and things like that. And so if TPT is too high, the temperature, plasma never reached that temperature and you never produced monopoles. And so you can play games like decreasing couplings or changing G star to sort of make this an effect. For sort of fiducial values, we basically got 10 to the 15 roughly. So you would say, at least for standard model unification, it'll pass everything. For SUSY unification, you'd be like, well, maybe the temperature never got high enough to do anything. Okay, so that was essentially all I wanted to tell you guys about today. So to conclude, basically, what I was talking about today was in the early universe, the evaporation of black holes is not in a vacuum. It's surrounded by a plasma. And the effect of the plasma doesn't do much to the evaporation of the black hole itself because it's colder than the black hole, right? It's 1% of its temperature. It doesn't stop the black hole from evaporating or anything like that. But it can get very hot, like 1% of the temperature of the black hole. And if the black hole is M Planck, 1% of M Planck is still a huge temperature. And this radius falls rather slowly. And so this plasma can actually be much more important than the black hole itself. And whoops, the example I sort of talked about today was basically monopole production. And monopole production is something that black holes never do themselves, but the plasma surrounding a black hole can produce monopoles. And in fact, it can produce it so efficiently that it can even overclose the universe and sort of give these really tight constraints on the reheat temperature. If the black holes are reheating the universe, if there was some subdominant thing, then they can produce some observable amount of monopoles, which again, depend a lot on if they do things like catalyze proton decay and whatnot. But it's actually black holes are a very efficient way of producing monopoles. Kind of a surprise. All right, thanks.
Thank you very much for the interesting talk. It seems there are many things we can do around these evaporating black holes.
Yeah.
Any questions from the audience?
Yeah, so you could also put the constraint on the number of black holes.
Yes, that's right. So if I just said, I know the number, I can say, let's say I have baryon number decaying or violating black holes. So the ones that destroy protons, those are the most constrained. You could place a very stringent constraint on the number of black holes that evaporated in the early universe.
I see.
And if you just say that it's like, oh, the Parker bound, you get a slightly weaker number, but you still get quite a stringent constraint on the number density of these guys.
Yeah. So I had another question, which is sort of maybe tangentially related. So if you have this population of black holes, say maybe all of the same mass, then they'd start merging and then they would be cooler because they're larger black holes. So is it known, like, how does a gas of black holes behave?
So this has been studied. People have actually, because people were like, well, what if these binaries that we're observing were all primordial and they came because in the early universe, they were close enough to get bound, gravitationally bound. So people have actually studied this. And the statement is roughly speaking that in general, the average black hole will not ever see another black hole in its lifetime.
Oh,
It's a rather small subpopulation. And the rough reason for this is that when the black holes are produced by taking a whole lot of gas and just like crunching it. But if you take that, what's the average velocity of that guy? It's been averaged over so many particles that they're essentially all at rest. And so that they don't, then Hubble expansion pushes them away faster, roughly speaking, than they're attracted to each other. And so they needed to have just been a rare fluctuation where they're formed really, really close, and then they could be gravitationally bound and start merging and things like that. And so the statement is, it actually does happen, like you said. It's just a rather small subpopulation of them.
Okay.
Yeah.
Any other questions? I have a question. Maybe I missed something there, but it seems the number of monopoles around each black hole is independent of the mass of the black hole.
Yes, that's right.
Why is that?
And so that's roughly speaking because the temperature, let me see, temperature profile, it's cooling. So this temperature profile around a black hole, let's find some derivation of R to the 7/11. This temperature profile is independent of the mass of the black hole. The reason is that the freeze out temperature here is fixed by when the black hole was just leaving equilibrium with it. But that fixes the mass of the black hole. And so at that radius, if you ask what is the temperature at some radius of 5 meters away from the black hole, you know exactly what the temperature and mass of the black hole was at that time. So it doesn't care about the initial mass, the initial temperature, or any of that. So the temperature profile around every black hole is exactly the same, independent of its mass. And that's why it ends up being, which is kind of a weird thing.
Yeah.
But it has to do with just like, in the end, a lot of the weirdness of black holes boils down to the fact that it's negative specific heat, so that it's getting hotter as it evaporates. And so it gets hotter, but then its lifetime gets a lot shorter. And so that sort of combination of things just sort of give this weird thing where it's just, because it's independent of the mass of the black hole at that radius, the only thing it can depend on is M Planck. So that this final temperature distribution can only depend on M Planck and R, because the mass of the black hole was fixed when it was freezing out at that radius. And so then the only other dimensionful parameter in this story is M Planck. And so M Planck just has to make up the dimensions, which means this is ridiculously hot, right? Like you're putting one of the largest dimensional analysis numbers you can think of in the numerator here. And that's why it's basically fixed from each black hole, is because each black hole has exactly the same temperature profile, which means it generates exactly the same number of monopoles. So a lot of very small black holes are very deadly. Even a few large ones are a lot less deadly, even though they might have the same total mass of the two situations. Yeah, it's a weird thing.
Now, Helling, you were looking at some temperature profile plasmas outside the black hole. Were you doing that?
No.
Some simulations of the plasma outside? No?
Oh yeah.
Some under density?
Yeah, but that's a different thing.
Right.
Yeah, that's the evolution of radiation density outside of black hole. I didn't consider evaporation.
I see.
But what if a black hole finishes the evaporation, say today, instead of in the early universe?
So today, Well, I guess it's an estimate I actually didn't show, which is basically how long does it take to even start to set up this profile? And so if it was today, basically what happens is the energy density in the plasma or like the gas is so dilute that it just takes too long to set up this profile. And even if it did set up the profile, notice that profile is determined by T black hole. And so we would need to be able to see Hawking radiation temperatures before we could even sort of see the profile around it. And so it's sort of, in some sense, in this case, it's a bit of a hopeless for black holes today, because we can't even see T black hole. So seeing stuff even colder than that around the black hole is even harder. Yeah, and I didn't consider anything like in astrophysical black holes where there's like merger events, where there's accretion of plasma that can totally screw up all this equilibrium distribution that I sort of discussed. And so in some sense, the early universe is much nicer because it was much more homogeneous and not all this crazy stuff had happened yet.
I see. Thank you.
Yeah.
Any other questions?
No, this was very interesting.
Yeah, very interesting.
Yeah.
If no, let's thank Anson again.
Okay. Thank you, Anson.
Yeah.
Thank you.
It was a lot of fun talking with you guys.
Yeah.
See you.
Hope to see you sometime.
Yeah, hopefully in person next time.
Yeah.
All right. Yep. See you guys later.
Bye-bye.